Okay, so welcome back to our SPI Doppler Review series. Now that we've explored the equations governing blood flow, we're ready to connect the physics to ultrasound. So in this episode, we focus on phase 4 Doppler fundamentals. And this is where motion becomes frequency shift. We'll break down the Doppler effect, Doppler shift, and the Doppler equation, examining how flow, speed, operation frequency, and Doppler angle determine what we measure. Understanding these principles is essential because Doppler is not just about detecting movement, it's about accurately interpreting how motion translates into measurable frequency changes. So when you clearly understand what affects Doppler, the Doppler shift, and what does not, the SPI questions again become systematic instead of confusing. So let's move from the physics of blood flow to the physics of sound interacting with motion. And now that we've worked through hemodynamic equations, let's step back and look at the full progression of phases. We began with fluid basics, building and understanding what blood is and what allows it to move. Then we examine flow types, identifying the different patterns blood can take within a vessel. After that, we moved into hemodynamics, where physics explained those patterns, connecting pressure, resistance, radius, and flow mathematically. Today we transition into Doppler physics or Doppler fundamentals. If hemodynamics explained how blood moves, Doppler physics explains how ultrasound measures that movement. And this is where motion turns into frequency shifts. The Doppler effect, the Doppler shift, angle relationships, and the Doppler equation all come into focus here. So once Doppler physics is clear, we'll move into signal processing next, where those frequency shifts become waveforms on a screen, then into instrumentation, where system settings influence what we detect, and finally clinical application, where everything comes together in real diagnostic practice. So each phase builds logically from the last, and right now we're shifting from the physics of blood flow to the physics of sound interacting with motion, which is the Doppler fundamentals. Okay, now that we arrived at the core of Doppler, what it is, or what is it actually? So we begin with Doppler effects, the overall principle that a change in frequency occurs when there is motion between a source and a reflector. And from there, we narrow it to the Doppler shift, which is the specific difference between transmitted frequency and the received frequency. And that shift is what we measure. Next, we examine what the Doppler equation relates, how velocity, transmitted frequency, cosine of the Doppler angle, and the speed of sound in tissue looks like. And this equation is the mathematical bridge between motion and measurable frequency change. Just as important is understanding what the Doppler shift does not depend on. So recognizing what does not influence the equation helps eliminate distractors on the SPI exam. We'll also clarify what happens with motion toward the transducer, producing a positive Doppler shift. Then we analyze angle relationships. What happens to the Doppler shift at 60 degrees? Why a greater Doppler angle produces a smaller shift? And why angles above 60 degrees become unreliable for accurate velocity calculations. And finally, we'll address total reflection below the 30 degrees and why angle selection matters, not just mathematically, but physically. So this is your physics core. Let's not rush this section. We got a lot to get through. So when you truly understand how angle, velocity, frequency interacts, Doppler questions stop being intimidating and start being predictable. Okay, so let's look at the first question. A change in frequency caused by motion of a source or reflector defines what? A says Doppler shift, B says Doppler effect, C is spectral analysis, and D is Poiseuille's equation. So again, the correct answer for this one is B, the Doppler effect. And the definition given is a change in frequency caused by motion of a source or a reflector. That describes the Doppler effect. The Doppler effect is that phenomenon, the overall physical principle that motion causes a frequency change. So why not Doppler shift? Right, so A isn't correct because the Doppler shift is the amount of the frequency change. It's the numerical difference between transmitted frequency and received frequency. So Doppler effect is equal to concept about the phenomenon, and Doppler shift is the measurable frequency change. That distinction is what this question is testing. And why are the other ones wrong? So C says spectral analysis. Spectral analysis is that display of the Doppler frequencies over time. And so the waveform that you see on the screen, it analyzes the Doppler shift. It does not define the frequency change phenomenon itself. Now, Poiseuille's equation relates to flow, it relates to pressure, it relates to radius, viscosity. It has nothing to do with frequency changes. It's a completely different physics domain. And so the big concept here is that if motion causes a frequency change, that relates to the Doppler effect. If you measure how much it changed, that relates to the Doppler shift. Okay, let's look at the next question. The difference between the emitted frequency and the echo frequency returning from a moving scatterer is called what? The answers are A, Doppler effect, B, Doppler shift, C, Doppler shift again. I think I had a problem on this one. D, continuity rule, and then B, Bernoulli effect. Okay, so I have to apologize for the lettering, the numbering here, but the correct answer is the Doppler shift, which is B and C on this one. So the Doppler shift, again, is the actual numerical difference, the transmitted frequency and the received echo frequency. So Doppler shift is equal to received frequency minus transmitted frequency. And it's the change in frequency caused by motion. So that shift is what we plug into the Doppler equation to calculate velocity. And so when the question says difference between frequencies, it's literally defining the Doppler shift. A is incorrect, the Doppler effect. Remember, this is a tricky one because it sounds almost the same. The Doppler effect is the overall phenomenon that occurs when there is a relative motion between source and the reflector. So it describes a concept that motion causes a frequency change, but it is not the same of the actual difference in the frequency. So think of it like this: Doppler effect relates to the event, Doppler shift relates to the measured change. And so the question is asking for the difference itself, so it has to be the Doppler shift. Now the other one, the continuity rule, this one describes conservation of mass and constant flow. So it has nothing to do with frequency changes, completely unrelated to ultrasound frequency shifts. And then the last one, the Bernoulli effect. So Bernoulli describes relationships again between pressure, velocity, height. It applies to fluid dynamics, not to ultrasound frequency changes. And again, I apologize for the lettering on the multiple choice answers. So the next question is, the Doppler equation relates the Doppler shift to the what? And answer A is pressure and resistance. B is flow speed and frequency. C is flow speed and pressure. And D says flow speed and resistance. So the correct answer here is flow speed and frequency. The Doppler equation is, right, F sub D, the Doppler frequency, being equal to 2 times F sub naught times V cosine theta divided by C, where F sub D is the Doppler shift, F sub naught is the transmitted frequency, V is the velocity of blood, or the flow speed, theta is that Doppler angle, and C is the speed of sound in tissue. Now, look at what's in the equation. Velocity, flow speed, transmitted frequency. So the Doppler shift depends directly on how fast blood is moving, what frequency you transmitted, and that's why the correct answer is flow speed and frequency. Let's go look at the other answers and determine why they are incorrect. So when you're looking at the first one, pressure and resistance, pressure and resistance are part of fluid dynamics, right? Poiseuille's law, not ultrasound physics. So the Doppler equation does not include pressure or resistance. Those affect flow indirectly, but they're not variables in the Doppler equation. The next one is C, which says flow speed and pressure. So velocity is part of the Doppler equation, but pressure is not. So pressure affects velocity in the body, but the Doppler equation itself does not measure or induce pressure. So this mixes hemodynamics with ultrasound physics. And the last one was D, flow speed and resistance. So again, resistance affects velocity physiologically, but resistance is not in the Doppler equation. The Doppler system measures frequency shift and calculates velocity, and it does not directly measure resistance. Okay, so the next question, Doppler shift does not depend on the blank. And the answers are as follows. A, flow speed, B, flow direction, C, operating frequency, and D, Doppler angle, or D, Doppler angle. And the correct answer here is B, flow direction. So the Doppler shift depends on, if you look at the formula, F sub D being equal to 2 times F sub naught times V times cosine theta, all divided by C. And again, as a reminder, F sub D is the Doppler shift, F sub naught is the operating frequency, V is the velocity or the flow speed, theta is the Doppler angle, and C is the speed of sound. But notice what is not in the equation. Direction by itself. The equation uses cosine of the angle, not direction as a separate variable. So direction only changes the sign of the shift, either positive or negative, not the magnitude of the shift. And that's the key here. Now let's talk about why the other ones are wrong if we want to break them down. A says flow speed. So velocity, designated by V, is directly in the equation. So as speed increases, Doppler shift increases. So no speed equals no shift. So it absolutely depends on flow speed. The next one, the operating frequency. Operating frequency, denoted by F sub naught, is also directly in the equation. So higher frequency relates to larger Doppler shift for the same velocity. So this definitely affects it. And the last one, Doppler angle. So cosine of the Doppler angle is again also in the equation. So at 90 degrees, this relates to cosine 90, which is equal to 0, meaning you have no Doppler shift. So in this case, the angle is critically important. And there's a trick to learning this if this gets you confused. Um, Relate direction with angle. Direction only determines whether the shift is positive or negative toward or away the transducer, but the magnitude of the Doppler shift does not depend on direction as a separate factor, which is why B is correct. Let's continue with the next question. So the question says, motion toward the transducer demonstrates what? A says spectral broadening, B is flow below the baseline, C is a positive Doppler shift, and D is an antigrade flow pattern. Of course, the answer is highlighted for you there. It's the positive Doppler shift, which is C. Again, my apologies for leaving that highlighted. So think about this. When blood moves toward the transducer, the reflected frequency increases, the Doppler shift is positive. On spectral Doppler standard display, the waveform appears above the baseline. And that increase in frequency equals a positive Doppler shift. And so let's look at why this happens. Just a quick physics recap. If you go back to the Doppler equation, F sub D equal to 2 times F sub naught V cosine theta, all divided by C. The flow is toward the transducer when cosine theta is positive, and the frequency shift is positive. So the machine displays it as a positive value. Now let's look at why the other ones are wrong, what those other answers even mean. So A says it's spectral broadening. Well, spectral broadening refers to vertical thickening of the tracing and or a wide range of velocity. So it has nothing to do with direction. B says flow below the baseline. Below the baseline represents motion away from the transducer, so that's a negative Doppler shift. So this is opposite of the correct answer. And then D, an antigrade flow pattern. So antigrade means normal direction of flow in a vessel, and that depends on anatomy, so not on the transducer position. So flow could be antigrade and still appear above or below baseline depending on the probe orientation. So this is also not the correct answer or the best answer. So if you think toward the probe, relating to a positive shift, relating to above the baseline, and then away from the probe, relating to a negative shift, which relates to a negative baseline. Okay, so we are on the next question, and the question says, a Doppler shift at 60 degrees is blank what it would be at 0 degrees. And so the answers are twice, so it'd be twice what it would be at 0 degrees. B says 1/2 of, C is 3 times, and D says 2/3 of. And so the correct answer is B, so it's 1/2 of what it would be at 0 degrees. Again, just look at the equation. The Doppler equation includes the cosine of the Doppler angle. So the Doppler frequency would be proportional to cosine theta. So the cosine term is everything here. So at 0 degrees, cosine 0 is equal to 1. And so at 0 degrees, you get 100% of the Doppler shift. And this is the maximum possible shift. Step 2, if you think about at 60 degrees, if you relate this to that, cosine of 60 is 0.5. And so that means the Doppler shift is 0.5 times the Doppler shift. So in other words, 1/2 of what it would be at 0. Why are the other answers wrong? So twice, cosine never makes a Doppler shift larger than at 0 degrees. And so 0 degrees is the maximum and you can't exceed it. 3 times, so that's again impossible. Cosine values range from +1 to -1. You can't get 3 times the shift. And the other one says 2/3 of, so cosine 60 is not 0.67. If you calculate it, it's 0.5. And so that's why that's incorrect mathematically. So you can memorize some values of cosine that would help you on the test. If cosine 0 being equal to 1, cosine 30 being equal to 0.87, cosine 45 is equal to 0.71, cosine 60 is equal to 0.5, and cosine 90 is equal to 0. So 60 always cuts the Doppler shift in half. So there's a clinical connection here. So this is why velocity errors increase dramatically at higher angles. So at 60 degrees, you're already working with only half of the maximum possible Doppler shift. So above 60, things become very unstable. Okay, so the next question says, for a given flow, the greater the Doppler angle, the blank. And the answers are A, less the Doppler shift, B, higher the operating frequency, C, lower the speed of the scatterer, or D, more accurate the Doppler information. More accurate the Doppler information. So the answer here is A, less the Doppler shift, right? Remember or memorize the equation. Go back to the Doppler equation. F sub D is equal to 2 F sub naught times V times cosine theta, all divided by C. So again, notice again, what's in there is the cosine theta. Now remember, we think about what happens to cosine as the angle increases from 0 to 90 degrees. So cosine 0 is equal to 1, cosine 60 is equal to 0.5, cosine 90 is equal to 0. And as the Doppler angle increases, the cosine value increases. If cosine decreases, the Doppler shift decreases. So for the same flow velocity, larger angle relates to smaller Doppler shift. And that's why we try to keep the Doppler angles at 60 or less. Okay, let's eliminate the others now. So B says higher the operating frequency. So operating frequency F sub naught, that's determined by the transducer, not the Doppler angle. So changing the angle does not change the machine's frequency. So this answer mixes up 2 independent variables. The next one, C, says the lower the speed of the scatterer. So blood velocity, right, little v, does not change just because you tilt the probe. The scatterer, the red blood cell, is moving at the same speed in the vessel. So only the measured Doppler shift changes, not the actual velocity. And the other answer, D, more accurate the Doppler information. So actually the opposite is true. As the Doppler angle increases, remember we said this, the angle errors cause larger velocity calculation errors. So accuracy decreases, especially above 60 degrees. So greater angle equals less reliable information. Okay, so the next question. Doppler measurements are not reliable at Doppler angles greater than blank degrees. We've said this over and over again in this series, but let's look at the answer and talk about all of them all over again as a review of Doppler physics. A is 30 degrees, B is 40 degrees, C is 50 degrees, and D is 60 degrees. So we've already said several times that, well, the answer is D, 60 degrees. Doppler measurements become unreliable at angles greater than 60. And let's go ahead and talk about this one more time. Now again, remember to memorize this equation, and let's look at the physics behind it. The Doppler equation is F sub D is equal to 2 times F sub naught times velocity times cosine theta, all divided by C. So the critical part in this equation here, or this question, is the cosine theta. So as the Doppler angle increases toward 90, cosine gets smaller, so the Doppler shift gets smaller. So small angle measurement errors cause huge velocity errors. So here's the key. At 60 degrees, again, cosine theta is equal to 0.5. At 70 degrees, cosine 70 is going to be 0.34. At 80 degrees, cosine 80 is equal to 0.17. So you see how dramatically it drops? Above 60 degrees, you have tiny changes in angle that cause large changes in calculated velocity. And that's why accuracy collapses above this. Um, so yeah, so if you plotted it, you would see a curve, a linear, nonlinear curve. And let's look at why the other answers are wrong, just by looking at the same logic that we use. So at 30 degrees, this is actually excellent for Doppler accuracy. So cosine 30 is 0.87, if you remember from the little table we gave you. So strong, you have a strong Doppler shift, and it's again very reliable. If theta is equal to 40 degrees, again still very reliable. Cosine 40 is about 0.77, so very little accuracy issue here relative to angles above 60. Even at 50, cosine 50 is 0.64, and so this is still clinically acceptable. And 60, that's the clinical cutoff. It's considered the upper limit of the acceptable Doppler angle in vascular ultrasound. So beyond 60, velocity calculations become unstable, angle correction becomes error prone, more error prone, and measurements become unreliable. So that's why vascular labs aim for 30 to 60 degree range. Okay, let's do this very last question in this series. And so it says, the question is, sound reflects totally at the wall-blood boundary, hence the Doppler angle is less than blank degrees. So A is 30 degrees, B is 40 degrees, C is 50 degrees, and C is 60 degrees. So let's look at the big idea here first. So when ultrasound hits a boundary between two materials, like vessel wall and blood, whether it reflects or transmits depends on the acoustic impedance difference of the angle of incidence. So as the Doppler angle gets smaller, more perpendicular to the wall, reflection increases. So at very small angles, the beam doesn't transmit into the blood. It reflects completely. So that cutoff happens at about 30 degrees. So the answer is most likely, the best answer here is 30 degrees. And why 30 degrees is correct, so again, angles less than 30, the incident beam is steep enough relative to the boundary that total reflection occurs at the wall-blood interface. So that just means that no useful Doppler signal from blood is apparent here. The beam never meaningfully enters the bloodstream, and you're basically bouncing off the wall, and this is why Doppler measurements are between, ideally, 30 to 60 degrees. If you go below 30, you risk excessive wall reflection and poor data. Now let's look at the other answers and why they're wrong, and we'll go through these one by one. B says 40 degrees. So if total reflection happened below 40 degrees, we wouldn't be able to obtain Doppler signals between 35 or let's say 38 degrees, but we absolutely can get Doppler at 40. So like in fact 45 is commonly used in vascular imaging. 40 is again too high here to have that total wall boundary reflection. If it's 50, kind of the same issue. Definitely too high. If reflection were total below 50 degrees, so almost all clinical Doppler angles would fail. So most carotid exams, which are typically between 45 and 60 degrees, they wouldn't work properly. But they do. So 50 degrees cannot work for this question. And then D, 60, that upper limit. This one kind of really falls apart. So at 60 degrees, this is the upper recommended Doppler limit for accurate velocity calculations, not a reflection cutoff. So total reflection occurred, if it occurred below 60 degrees, Doppler imaging would basically be impossible in clinical practice. So every vascular lab would be in chaos. 60 degrees just doesn't uh, make physical sense for total reflection at the wall interface. Right? So this is just looking at it conceptually. If you did like a visual intuition, think of skipping a rock on water. Very shallow angles reflects skipping, right? Steeper angles, that enters the water. So ultrasound behaves similar at tissue interfaces. Below about 30 degrees, the behavior of the beam is more like that of the shallow skipping. It reflects rather than transmits. And there's a good clinical connection here. And this is what they're testing here with this question. The question is really testing whether you understand why we avoid very small Doppler angles and why angle correction matters. So why less than 30 degrees is problematic. Again, it's not a random trivia. It connects directly to how you position the transducer in vascular scanning. That's why you spend most of your academic career practicing scanning and not physics.